Hey, welcome back to Fan Mama Physics. In this video, we are going to continue with electromagnetic induction, looking at the EMF induced in a long bar of conducting material, okay, as it's moved through as a sweep through a magnetic field. In other words, motional EMF, okay? So let's take a look at example 1, and example 2 would be in the next video. In this following figure, we have a magnetic field going, looks like out of the page. It's going to be 0.8 in field strength. Okay, so this is where part of the question got cut off, so we're going to fix it. Okay, so it says here the magnetic strength is 0.8 Tesla. The rod speed is 10 meters per second. So let's add this here. That's pretty fast rod. Okay, the length of the rod is 0.2 meters. And the resistance of the resistor is 2 ohms. And what else got cut off? The resistance of the rod and the rails are negligible. So that is the that's the wire here. So that includes this wire, not the light bulb, of course, but this rod here. We're going to assume that the resistance is going to be very small in comparison. Okay, so the first question is, find the induced EMF in the circuit. Induced current in the circuit with direction and power dissipated by lamp. Okay, not too bad. So let's go with the induced EMF in the circuit. So first of all, we're going to look at motional EMF. That is going to be in your data booklet. That is going to depend on the magnetic field. It's going to also depend on the length of the wire, as well as the velocity of the moving rod. So that changes. So it actually shows very well in this diagram that as this rod is moving, it's sweeping through the magnetic field. It's changing the area, or how many magnetic field lines are going through this wire. So that changes the magnetic flux, which then induces an EMF. So this is motional EMF. It's just another way of describing Faraday's law. And of course, applying Lenz's law to figure out the direction of the current, which we will do later in this question. Okay, so let's quickly put this one in. Magnetic field is 0.8 Tesla. The length is given, which is 0.2 meters. The speed is 10 meters per second. That's really fast. That's like 36 kilometers per hour. That's like driving in a neighborhood. Alrighty, so putting this all in, we're gonna get hopefully 1.6. Yeah, we got exactly 1.6 volts, okay? Alright, that was the first question. Not too bad. Just plugging and chugging. The induced current in the circuit and direction. So the current arises because the current produced, of course, is due to the fact that we have an EMF, so we have a potential difference. And that's going to mean that we're going to have a current going through this resistor, which the resistance is given. So according to Ohm's law, V equals IR, we can use that to figure out the current through that resistor, which is going to be V over R, in which V, what we found, 1.6 volts divided by the resistor of 2 ohms, and that's just dividing that by half, so that's going to be 0.8. 0.8 and 2 sig figs, 0.08 amps, okay? So let's figure out the direction of this, figure out the direction of the current. So there's actually 2 ways. I'm going to explain 2 ways. I mean, will be hard to use a right-hand rule because of the camera and mirroring effect. We'll try our best. Okay, so I would suggest you do this along with me, okay? So have your right hand out in front of you, and so put your pen down if you have your pen in your hand. Don't use your left hand thinking you can cheat your way out of this. Only right hand works, okay? So we're going to do this first way. So we're going to use this one that looks like this, okay? It looks like you're trying to middle finger someone, but you actually aren't, because you're trying to hide the middle finger away, okay? So hopefully you know this already. We're just going to apply it, okay? So first of all, we have imagine there are charges in the metal. let's say, since we're working with conventional current, let's just work with positive charges. So these positive charges are going to move towards the right on your page. So that's going to be your thumb. Your thumb is going to be the direction of movement of the charges. Your index finger is going to be the direction of the field. Okay? So if we take a look here, the field is going out of the page. So you should be poking yourself with your middle finger as you're doing this. Okay? So my thumb, of course, on your screen will look like the opposite. My thumb is going to point towards the direction of the velocity. So that's the green arrow for a positive charge. The field is, oopsies. Actually, no. It's not my middle finger poking me. It's gonna be my index finger poking me. So it's like you're pointing at yourself. So your index finger is gonna be the field that's gonna point towards yourself. And then your middle finger, you look like you're middle fingering yourself, but in upside down. Okay, so your middle finger is actually gonna point down the page. So that's the direction of the magnetic force acting on these charges, okay? So that's the direction of the force acting on these charges, which will cause the charges to move down. So that's assuming positive charge carriers. So that's going to be the direction of our conventional current, okay? So that's one way to do it. The other way to do it is also to, the other way to do it is to the other right-hand rule is just a thumbs up, okay? So the curl and the thumbs up. In this case, applying Faraday's law. Applying Faraday's law, think of it this way. The bar is getting swept towards the right, which means the magnetic flux linkage will increase going out of the page. So to counter that increase, our magnetic field induced by a current has to be pointing into the page. So into the page, notice your fingers with your thumb going into the page. Notice your fingers are curling in the clockwise direction. And going clockwise, we notice that it's exactly what we predicted or what we figured out previously with the other right-hand rule, which we'll use to predict the motion using the magnetic force acting on charges. Okay, so here B, the direction of the current around this loop of wire is going to be clockwise. Okay, so there you go. That was B. Let's do C. Last but not least, figure out the power dissipated by the lamp. Okay, so whenever I calculate power dissipated by something, I always like to use the current going through that resistor as well as the resistor itself. So this is the one preferred. I squared R, in which the current we figured out previously, 0.8 amps squared times the resistor, which is 2 ohms. And then putting this one in, we're going to get 1.28 exactly. And this is power, so our units are going to be in watts. Okay, so there we go. That's example 1. So hopefully you have a better idea of how this, how the motional EMF works. I have another video coming up with an airplane also applying motional EMF. So hopefully this was helpful, and thank you for watching. Maybe stay tuned for the next example. That Mama Physics signing out.